So in this video, we're going to look at Taylor polynomials. A Taylor series is a power series, but it's not derived using the geometric series formula, but it's derived using derivatives. And so we see this formula here. Essentially, we're using the function evaluated at the center where we're interested in it, and doing the best estimates. And then we're adding on derivatives, first derivative, second derivative, third derivative, and so forth, also evaluated at that same point and being multiplied by powers of this linear factor x minus c. If we use 0, this is a special case called a Maclaurin series, but a Maclaurin series is just a subset of the Taylor series. It's simply that the Maclaurin is centered at 0 and the Taylor series can be centered anywhere, including 0, but also other places. And basically, if you think about these first two terms of this Taylor polynomial, you are just doing a linear approximation. But as you add additional derivatives, then you're still doing the same kind of thing. You're still doing an approximation, but you're doing it with higher powers. And so your estimate will be better longer. And so conceivably, you can do this for an infinite number of derivatives if your function is differentiable an infinite number of times. Taylor polynomials are also really useful tricks for rewriting a finite polynomial in terms of a particular center. So this is actually something that will come up later on in other courses, that you can actually use this. Let's say you have a degree 5 polynomial and you want to rewrite it centered at 2. You can do that without having to do quite as much sort of algebra. Doing it for a linear, even a quadratic, isn't too bad. Doing it for a cubic or fourth degree or something like that, the Taylor polynomials are really useful for doing that. Now, there is also a remainder term every time you stop your Taylor polynomial, your Taylor series at a particular point. There's going to be an error associated with that. And the remainder term is given by this r sub n. Now, this is going to depend on a couple of different factors. For one thing, it's going to depend on the next degree term, but it's also going to depend essentially on some point inside of an interval. So you're going to have to specify how far away from the center you're making this estimate. In some functions, there will be a maximum over the whole function, like sine and cosine. But in other kinds of functions, you will need to specify an interval on which you're interested in estimating the error. We're going to look at an example of this in a bit. Now, your textbook has a list of elementary power series functions. They tend to be centered at 0. And so if you're shifting the whole graph, you can derive these. You can just, again, shift the Taylor series. But if you are trying to center them at a different point without shifting the graph, then you have to derive them from scratch. And so we're going to look at an example where we're going to derive these from the beginning. So I tend to use a table when I do this, just to help keep track of all of my individual pieces. But of course, your mileage may vary. So here I want to find the Taylor polynomial for the function e to the x, nice simple function. It differentiates forever, but I'm going to center it at 1 instead of 0, and I'm going to calculate 6 total terms, so n equals 5. So we're going to need the steps, the number of derivatives that we've taken. 0 just means it's the original function. For our formula, we're going to need the factorial, n factorial. I'm going to need the derivatives. So the 0th derivative, again, is the original function, and then the first derivative and the second derivative. And so you can fill out the table by taking your derivatives. And then to get the coefficient that you need for this, you're going to evaluate each of your derivatives at the center. So e to the 1 is e, and that's true all the way down in this example. And then the x minus c to the n term, that is going to depend on, again, your center is c, and then also your x minus c to the 0 power is just 1. And then x minus 1, x minus 1 squared, x minus 1 cubed, etc. And when we put all of those pieces together, here we're going to have e times 1 divided by 1 is going to be e. And then for this one, we'll have e times x minus 1 divided by 1 is e x minus 1. And then in this one, we'll have e times x minus 1 squared divided by 2 factorial, which is e over 2 x minus 1 squared, and so forth. Now, the polynomial itself is then just going to be the sum of all of these terms, which is going to be this expression. And then there is a remainder from where we drop off. We'll see in another video how these approximations work in graphically, but for right now, this is the polynomial expression. When you're writing these out, of course, if you're using the table, you can't just like circle the final answers. You need to write out the polynomial. Now, if we're doing a function like sine, then what we end up with, particularly if we're centering it at 0 or pi over 2 or something like that, one of those, standard angles, what we'll get is that some of the derivatives will be 0 and some of them will not. And so if you want a certain number of terms, you will have to go out a little bit further. So watch the way that the problems are stated. Here we're told we want n equals 6. So we'll go out to n equals 6. And then the error will be on the 7th calculation, the 7th term. But if we were doing this at a point that wasn't centered at 0 or pi over 2 or something like that, then these would not necessarily be alternating zeros. And so just be careful about what you're doing. This doesn't tell us the center directly, but it says it's a Maclaurin polynomial, so that means C is 0. So I filled out the table the same as I did the previous one. These are all my n's. And again, I went one step further in this one because we're going to estimate the value and then calculate the maximum error. So I went one further because that error term is going to depend on that next term in the sequence. These are my factorials, and then I take my derivatives. Again, the 0th derivative is the original function, and then the first derivative, the second derivative, the third derivative, and so forth. And then I evaluate it at the center. So sine of 0 is 0, cosine of 0 is 1, sine is 0 again, negative cosine of 0 is -1. And again, you see this pattern get established with the sine and cosine functions. And then since we're centering it at 0, x to the 0 is 1, x minus 0 is just x, and so forth. And so when we put everything together, the terms where the coefficient is 0 are still themselves 0, but the ones where you have a 1 or a -1, you end up with alternating signs and odd powers. And so the polynomial itself is just x minus 1/6 x cubed plus 1/20 x to the 5th. There is actually no 6th degree term because that coefficient is 0. And then we have a remainder on the next term. Now, because we were asked for n equals 6, the error starts with n equals 7. And this f of the next derivative evaluated at z. Again, remember, this is essentially, there is some point in an interval, or there's some point on the function. They're essentially referring to the maximum value here. Because we're making an estimate. We can't know what the exact error is going to be without actually knowing the exact value of the function. So this is representing the maximum absolute value on some interval. Now, because sine and cosine have a maximum of 1 on the entire number line, the entire real number line, we can always make this statement that the absolute value is less than or equal to 1. And so that component is just going to be 1. The 7th factorial is in our denominator, and then x to the 7th is going to tell us, again, how far away from that center are we making our estimate in order to calculate that error. Now, if we plug in the pi over 4, for instance, we can not only evaluate the polynomial at that point, but we can estimate the error. So here we will plug in the pi over 4 into the polynomial, and this is the x, this is our x cubed, this is our x to the 5th. When you plug that into the calculator, you get something about this. And we know that we're supposed to get 1 over the square root of 2. So this actually does look somewhat similar to 1 over the square root of 2. And then we can calculate our error by plugging in pi over 4 to the 7th into our error term. And this is very similar to the true value of the error when you actually compare this to 1 over the square root of 2. Now we are making an estimate, so the error estimate is slightly larger than the true actual error, but that's to be expected because it's an estimation. Now, as I noted before, if you do not have a function where there is like a sine or a cosine, where there's a maximum value on the whole function, then typically you have to specify an interval that contains both the center and the point at which you're doing the estimate in order to get this estimation. And so often what we do is we pick a symmetric interval. So if we were estimating, for instance, this value pi over 4, we might choose the interval negative pi over 4 to pi over 4, centered at 0, since that was where we did our Taylor polynomial approximation. And then you could calculate the error using that bound. What is the maximum value of the negative cosine function, the absolute value of the negative cosine function on that interval negative pi over 4 to pi over 4. Now, in this case, you would still get the same answer because cosine is a maximum at 0, which is the middle of that interval. But for other kinds of functions, you will often get maximum at the endpoint, depending on whether it is a continuously increasing or continuously decreasing function.